Hello, everyone. Today, I will explain the comparison instructions in the TIA Portal programming software. First, let's look at the objectives of this lesson. 1. Explain the principle of comparison instructions. 2. Master the usage of comparison instructions. 3. Use comparison instructions to write control programs for buttons, indicator lights, and carry out online debugging. So, what are the types of comparison instructions? Comparison instructions are divided into several categories: two-parameter comparison instructions, value range comparison instructions, and validity check instructions. The two-parameter comparison instruction CMP is used to compare two numbers, IN1 and IN2, with the same data type. IN1 and IN2 are located above and below the contacts, and the operands can be variables or constants from the I, Q, M, L, D memory areas. Clicking on the instruction name, for example, double equal to brings up a drop-down list to change the comparison type. Clicking on triple question marks brings up a drop-down list to select the data type of IN1 and IN2. Double-clicking on the instruction parameters IN1 and IN2 double question marks allows you to input the corresponding addresses or values for IN1 and IN2. The parameter data types for the CMP instruction include word, int, etc. Refer to the table below for detailed information. The principle of comparing two parameters is: when two parameters IN1 and IN2 of the same data type meet the comparison condition, that is, IN1 is equal to, not equal to, a greater than, or equal to, less than, or equal to, IN2, the contact closes, allowing current to flow through. The types of comparisons for two parameters include equal to, not equal to, greater than or equal to, greater than, less than or equal to, and less than. Next, let's practically operate through the following example. When the value stored in MD100 memory is greater than or equal to 50.36, the contact closes, Q0.0 outputs 1, driving the load light. This program requires the use of numerical comparison instructions. Enter MD100 above. Enter 50.36 below, and select greater than or equal to for the comparison type. As the program involves decimal values, you can select real for the middle option. Then, add an indicator light Q0.0 at the end of the program. After inputting, compile and simulate the program. From the results, we see that the program did not run successfully. The load light did not turn on. What could be the reason for this? It's because the value in MD100 is 0, which does not satisfy the condition of being greater than or equal to 50.36, hence the load light did not turn on. If we change the value to be greater than or equal to 50.36, how would the program behave? Let's input the value 60 for MD100 and observe the changes in the program. For easier viewing, let's change the numerical format to decimal. From the results, we can see that the program now runs successfully. The load light turns on, and Q0.0 outputs 1, indicating the correct program implementation. This concludes the programming example 1. Next, let's familiarize ourselves with another case. When the value stored in MW20 memory is greater than 300 and less than or equal to 1000, Q0.1 outputs 1. When the value stored in MW20 memory is less than or equal to 300 or greater than 1000, Q0.2 outputs. Following the example above, input the relevant data in program segment 1. Ensuring the selection of the data type as INT to avoid errors. Continue inputting data in program segment 2. Noting the presence of or in the problem statement, which requires forming a parallel branch below. After verifying the data and format, proceed to simulate the program. From the results, when MW20 is not assigned a value and is 0, segment 2 of the program satisfies the comparison, leading to Q0.2 outputting 1. Adjust the numerical format to decimal. Then change the value in segment 1 to MW20 equals 500, which satisfies the comparison condition, resulting in Q0.1 outputting 1. Moving on to value range comparison instructions, which include within range and out of range instructions. The working principle is, if there is current flow into the instruction box, the comparison is executed. Otherwise, it is not. If the comparison result is true, the function block outputs true. The graphical representation. Min represents the lower limit of the range. Max signifies the upper limit. And VAL represents the comparison value. If the input at the function block input is 1, the comparison instruction is executed, otherwise, it isn't. The function block output indicates the comparison result. True outputs 1. False outputs 0. For detailed information on parameter data types, refer to the table in the presentation. Let's now look at the following example. Write a program to achieve the following. Store data greater than or equal to 300 in MW200 memory, and when the value stored in MW40 memory satisfies MIN less than or equal to VAL less than or equal to max, output 1 on Q0.3. If the value stored in MW40 memory does not meet VAL less than or equals to MIN or VAL greater than max, Q0.3 should output. Continuing with practical exercises in the programming software. Following the problem statement, input MW200 above program segment 1 and 300 below it. Select greater than or equal to for the symbol, and change the data type to int. Choose IN range from the comparison instructions and add it to the program segment. Set a minimum and maximum value range, entering 157 as the minimum and 1500 as the maximum. The real-time value is the one stored in MW40. If the program meets the criteria, Q0.3 will output. Let's verify its accuracy. Through the software, it's evident that the program is not successfully connected at this point. To rectify this, Let's change the value of MW200 to 500 after adjusting the numerical format to decimal. This value satisfies being greater than the minimum and less than the maximum. And input 200 into MW40. Now the program is connected. From the program, we see that MW200 must be greater than or equal to 300 for the program to output. MW40's value must be within the minimum and maximum values to trigger an output. For easier viewing, let's adjust the display format of MW200 to decimal. This completes the first requirement of the problem. From this operation, we observe that when the input side comparison contact closes, executing the comparison instruction, and when MW40 is not initially assigned a value of 0, not satisfying MIN less than or equals to VAL less than or equals to max, the equivalent contact is disconnected, resulting in false. Thus, Q0.3 outputs 0. When MW40 is assigned a value of 200, satisfying MIN less than or equals to VAL less than or equals to max, the equivalent contact is connected, resulting in true, and Q0.3 outputs 1. Next, let's program for the subsequent requirements. Similarly, input MW200 is greater than or equal to 300. When the program satisfies being less than the minimum value or greater than the maximum value, Q0.4 outputs. Following the instructions, select out of range from the comparison instructions and add it to the program. Input the respective values and proceed with monitoring. Initially, with MW200 at 0, not within the range, we adjusted the value to 500, resulting in 0 as expected. Similarly, inputting 2000 also satisfies the condition. But 1000 falls within the range, hence not meeting the condition. To summarize the operations, when MW40 is not assigned a value of 0, satisfying VAL less than MIN, the equivalent contact closes, resulting in true, and Q0.3 outputs 1. When MW40 is assigned a value of 200, not satisfying VAL less than MIN or VAL greater than max, the equivalent contact disconnects, resulting in false, and Q0.3 outputs 0. This concludes our lesson for today. Thank you.